Let's do an example of Lenz's law. So what we've got drawn here is what I would call case 1, putting a north pole into a loop of wire. And then you can do for other cases, you can pull the north pole out, you could put the south pole in, you could pull the south pole out. So this arrow is indicating the direction of motion of the north pole of a magnet as I'm pushing it towards this circular loop of wire. We can consider the circular loop of wire to be facing to the left, but in order to see what's going on better, I have given it a little bit of a tilted perspective so that you can see this side of the loop is close to you and this side of the loop is further away from you. So these magnetic field lines are already going through the inside of the loop. These magnetic field lines have not made it into the inside of the loop yet, but with this motion, eventually those lines would push in through that area of the loop. So when we ask ourselves the first question from Lenz's law, what is changing? What is changing is the number of magnetic field lines through the area is going to be increasing. These will still be poking through that area, and this one's going to be poking through that area as well as more as we keep pushing that magnet into that loop. So we've identified that the number of magnetic lines through the area is increasing, and that means that the amount of flux through that area is increasing. We've identified what the change in flux is. There's an increase in the change in flux. As a result of this, both an electromagnetic force and a current are going to be induced now in this loop. And that current has to make a new magnetic field. The new magnetic field has to be made to oppose the change that we're talking about up here. And since this change in flux is an increase, the new magnetic field has to be made to reduce the amount of flux. So a reduction in the amount of flux is what opposes an increase in flux. We want to decrease the flux to oppose the increase that's happening by pushing in the magnet. So how do we do that with the new magnetic field that is going to be made? We want to reduce the amount of magnetic flux by adding in a new magnetic field which points against the direction of the original magnetic field. Then what's going to happen is when you add up opposite direction magnetic fields in flux, you're going to get subtraction so that you have a decrease in the amount of flux. That's how we are opposing this increase, is by trying to decrease the flux. So we've figured out the new magnetic field that's being made by the loop has to point against the direction of the incoming magnetic field from the magnet. So when we go back up and look at our diagram, this is the direction of the magnetic field from the magnet. Therefore, the direction of the new magnetic field has to be in the opposite direction of that. Now, the last step is, since we know the direction that the new magnetic field has to go, this is supposed to tell us with a right-hand rule which direction the current is going to flow around this loop. So remember with my perspective that I've drawn here, this is the close side of the loop, this is the far side of the loop. And I've got a magnetic field that points that way. The thing that I should be pointing with is my thumb. Thumb points this way in the direction of the new magnetic field. My fingers are then going to curl this way, which means on the close side, this side, the current is going to be going up, and then as I wrap around to the back side of the loop, the current should be flowing down. This will make the current flow round and round like this. So the right-hand rule that we've just learned is going to be telling me that this current should flow up this side and down this side. That is the direction now of the current that's figured out by using a right-hand rule. And how do I report that to somebody? Well, since I've made my drawing like this, you can have a perspective that is working with clock directions so that you can say this direction is counterclockwise. I would then report my result by saying, to make the new magnetic field go in the right direction, the current must go counterclockwise by the right-hand rule. Just tell somebody it's counterclockwise by the right-hand rule, and you've done it.